Good evening, ladies and gentlemen. Welcome to my presentation. My name is Axel Soldrindler and I'm working as a senior researcher at Woodke Plus in Tulln, Austria. And today I'm going to talk about bio-based porous structures based on cellulosic materials. Porous materials are widely used for different applications where different material criteria are needed. They perform as co-layers, for example, in lightweight materials for mechanical purposes, but their lightweight is also of interest for packaging when it comes to protect valuable goods during transportation. However, not only their low weight, but also their low thermoconductivity is of significant value. That is why most of insulating materials are of a porous structure. Besides lightweight and thermal insulation properties, a good fire resistance and moisture resistance are of advantage. Inorganic materials, like for example different silicates formed to a porous structure, exhibit such preferred material properties, but their production is quite energy consuming. A bio-based hybrid that exhibits inorganic properties would be straightforward. As an interesting raw material, we defined wheat bran, which is a side product of the wheat production, arising in enormous amounts and appears in flake-like structure. Wheat bran is the outer shell of corn and is full of different nutrition that are mostly used for horse fodder nowadays. The second material that we were using for our investigation is wood sawdust, what is arising in enormous amounts in wood panel industry. Nowadays, most of this material is used for fuel and is burned. As both raw materials are quite heterogeneous in their raw condition, we decided to use different disintegration techniques for homogenization. Therefore, we used a dry and a wet disintegration process in parallel. Here we used an ultra-centrifugal mill for the dry process and the ultra-friction grinder for the wet process. After the disintegration, the aim was to produce a porous structure by means of mechanical foaming with a certain amount of organic and inorganic material. We started with different organic binder systems as for example PVAC, ureaformaldehyde and starch glue, but also different inorganic silicates in combination with surfactants like twine and sodium lauryl sulfate to create foams. In the beginning, we were not able to create stable foam with a significant amount of inorganic binder, as the moisture content of the organic material involved turned out to be crucial. However, in the end we achieved a 5 times volume expansion with 50% organic particles and 50% inorganic binder material and were able to dry the foam to a stable porous structure. At the first picture you see such a dried porous structure based on wheat bran, wood and silicates with a density of approximately 100 kg per cubic meter. At the pictures below, a dried foam structure reinforced with fibers from the wheat bran and wood is visible. We found similarities in the fiber structure of the foam and the seed beard fibers that are usually found on every wheat corn outer shell. As the wet foam contains up to 60% water, the drying is a crucial step. Therefore, 3 different drying atmospheres, namely a standard climate, a moist climate and a dry climate, were established to see their influence on the porous structure's properties. Finally, we were able to cut out samples for further investigation. At this slide you see the raw density we achieved with the different drying atmospheres. Interestingly, the high moisture content resulted in a slightly lower density than the standard climate on the left side. The lowest density was reached with the higher temperatures. At the right side you see an indicator for the density range for commercially available inorganic foam glass. On this slide we see the thermoconductivity values in watts per meter Kelvin of the samples dried at the different climates. Here, the 2 samples dried with lower temperatures show no significant differences with values around 0.07 watts per meter Kelvin. Only the higher drying temperature achieved a lower thermoconductivity of below 0.06 watts per meter Kelvin and is therefore within the range of commercially available foam glass. Further, we conducted a single flame test where flame is held to the sample surface and the burning behavior is observed after the flame is removed. As reference material, we took cork and a wood fiber panel, both with a density of approximately 260 kg per cubic meter. What you can see is that our wheat bran sample did not burn after 30 seconds, where both of the other materials ignited and burned after the flame was removed. To conclude, we can say that we successfully produced a porous material based on wheat bran, wood sawdust and inorganic silicates with quite low density, proper thermal conductivity properties and good burning resistance. In future we want to conduct mechanical tests to analyze the compression resistance of the material. Thank you for your attention and enjoy the rest of the conference.